Okay, so we're going to talk a little bit about total internal reflection. You have covered this before in National 5, so you should be familiar with it, but we're going to revisit it as well, and we're also going to come across some new equations. So the practical here, and I'm going to link you to a video of the practical as well, is to investigate total internal reflection to find out what angle of incidence is the start of total internal reflection, and what angle of incidence is the critical angle. So the aim is to investigate the refraction and reflection of a ray of light emerging from a semicircular perspex block into air. Okay, so the rays involved here would be you would have an incident ray and an angle of incidence. You would also have a reflected ray. That's angle of reflection. We'll call that little r. And you would also have a refracted ray. So that, and an angle of refraction, which we'll call capital R. Okay, so what you do is you shine the light in at various angles of incidences, so the various eyes, and then you would measure the angle of refraction and also the angle of reflection. So you'd start off, and the angle of incidences that you would use are 10, 20, 30, 40, 50, 60, 70, 80. And you'd measure the angle of refraction. Now we know, because we've done this before, that the angle of the refracted ray at some point disappears. Okay, so there's a point where there is no more refraction and there's just reflection, and we know that that is the point of total internal reflection. So the point where exactly where the refracted ray becomes 90 degrees is called critical angle. So what I'm going to do is I'm going to put in some sample answers, sample data for you here. We know that the angle of reflection is the same as the angle of incidence, so we can write that in straight away. So it's just going to be 10, 20, 30, etc., etc. Okay. Now the angle of refraction. So the first angle, that's R, that's capital R, that's lowercase r, and that's I. So the angle of refraction at incidence of 20, the angle of refraction. Sorry, at incidence of 10, the angle of refraction is 20. At an incidence of 20, it's 27. Let's write that in. At 30, it's 47. At 40, it's 72. And at 50, there isn't a refracted ray anymore. So in between 40 and 50, the critical angle will be. Okay, so the critical angle will be between 40 and 50, because above 50, we don't have any more refraction, and below, and at 40, we do have a refracted ray. So the angle of incidence is always equal to the angle of reflection. We know that because that's the law of reflection. As the angle of incidence increases, the angle of refraction also increases. When the angle of incidence inside the perspex block is greater than, well, when I was doing the experiment, I found that about at 42 degrees, the angle of refraction was 90 degrees. So, and the angle of reflection obviously is 42. So when the angle of incidence inside the perspex block is greater than 42 degrees, there is no refracted ray. So when it's greater than 42, at 42 it's 90 degrees, but when it's greater than that, there's no refracted ray. So this angle is called the critical angle. If the angle of incidence is greater than this, the ray undergoes total internal reflection. Okay. Right, so theoretical determination of the critical angle. Now, we know at the critical angle, the angle of reflection is 90 degrees. So if that is at my critical angle, then I will have an angle of refraction. Did I say that's what I meant, refraction at 90 degrees. That's my angle of my refracted ray. And obviously also I'll have my reflected ray, which is the same as the critical angle. Okay. So just to remind you that that is at the critical angle. Okay, so at critical angle. Okay. If you shine light in above critical angle, then all you get is reflection. If you shine light in below the critical angle, you get reflection and refraction. So you get reflection, you also get refraction. Okay. So, but we're looking at the critical angle just now. So let's complete the diagram to show what happens to the ray of light when it's shone in at the critical angle. So we know that the refracted ray is 90 degrees. So in this case, remember N2 over N1 equals, get rid of that and we'll change it to N2 over N1 for a reason that I'm going to show you in a second, is sine theta 1 over sine theta 2. So in this case, we're looking at this point here. Okay, so our initial medium is the prism, sorry, the semicircular glass block. Okay, so N1 is the glass block and N2 is the air, because N2 is going from glass into air. Okay, so that's air, that's glass. So it's slightly different this time around because N2 is our air and N1 is our glass block. So N1, because we don't know what the refractive index is. So sine theta 1, so this is our angle in material 1. So sine theta 1 is sine C. And sine theta 2 is at 90 degrees because it's refracting to 90 degrees. So sine 90. Now, those of you that have memorized your trigonometry, you will know that sine 90 is 1. So we end up with 1 over N1 is sine of the critical angle divided by 1. So rearranging that, you end up with sine of the critical angle is 1 over N. So here, we can keep it with N1. So the critical angle is obviously the inverse sine of 1 over N. Let's rewrite the inverse sine. Just a little neater. There you go. So you can calculate the critical angle of something if you know its refractive index. And you can calculate the refractive index of something if you know its critical angle. So for perfects, N equals 1.5. So evaluate the critical angle using this formula and compare the theoretical value with your experimental value. Okay. So calculate the critical angle. We do inverse sine of 1 over N. So it's going to be inverse sine of 1 over 1.5, which is 41.8 degrees. And I got 42 degrees with my experiment, so I was relatively spot on for that one. Okay, so that's how you find the critical angle from the refractive index, or you can use it to find the refractive index from the critical angle. We have talked about this before in previous years. Optical fibres use total internal reflection to pass signals down a glass rod. Okay, so a total internal reflection of light inside a narrow glass rod allows light to travel from one end to the other, even if the rod is bent. And it says complete the diagram below. So all it wants you to draw in is basically reflection along the glass. So we've got reflection, total internal reflection. Okay, there you go. So light goes in, none of it gets refracted out, so none of it gets wasted, and it comes out the other end. And there are many uses of optical fibres, and I'm going to get you guys to have a look at those just